tracks, we'll be revisiting the motor cortex. We're going to look at the individual motor tracks. Oh, we're going to touch on this. We're not going to get into great detail here. And we're going to spend the majority of the day looking at problems with loss of function. Loss of function obviously is going to be very important for all of you in the future. So the actual motor cortex, if we want to think about that, primary motor cortex, premotor cortex, supplemental motor, somatosensory, parietal association in there. There's a tremendous interaction here. What you have to remember is every time you go to do something, every time you move, every time anything goes on with you, it's in response to a variety of sensory inputs, whether they are somatosensory inputs or special sensory inputs. There are a lot of inputs going on. We touched on the homunculus in the past. We are revisiting it. Please, at this point in time, I expect you to know the general layout here of both the motor and the somatosensory homunculi. We're revisiting inputs as they come into the cord. We're going to look at cord information, the movement of information through the cord as the day progresses. And we are going to look at a variety of, quote, motor systems. These are the 6 major motor tracks where signals are moving. You know, they're efferent signals. They're all starting somewhere in your brain and exiting. A lot of times in reality, unless there are any reflexes going on, you generate the signals for movement in the somatic motor system at the motor cortex. That's where the signal says do something. Now, in reality, what's going to happen is you can say move that arm. That's a very simple signal that's coming from the motor cortex. That signal is going to bounce all over your brain. There's a lot that happens getting the signal from there and ultimately out. It's going to bounce around, it's going to go back to the cortex, and it's going to leave. We'll be working on that over the next few weeks. So let's look at these tracts. We have the lateral cortical spinal tract. Movement of contralateral limbs. This for you should be probably the easiest of the tracts to really be aware of. This is what you think of when you think about signals coming from your brain. They leave your brain, they cross over, and they do something on the other side of your body. Now the rubrospinal tract starts at the red nucleus, not at the motor cortex itself. But once again, it's involved with movement of contralateral limbs, but exactly what's going on isn't fully understood. So that's the lateral motor system. In many respects, the lateral motor system involves your arms and legs. Okay, so that should be, I think, pretty straightforward for you. The medial motor system is a little more complicated. There's a lot more going on. Now, when you think about a body standing in front of you, you know, the limbs are lateral in anatomical position, and your core, your head down through your groin, pretty much, is medial. So we have the anterior cortical spinal tract, bilateral, axial, and girdle muscles. Axial muscles would be all of the muscles in your torso, down to your girdle muscles in your hips. Technically, your shoulder muscles are also girdle muscles. The vestibulospinal tract. Whoa, wait a minute, that's starting to make sense. Vestibulo. Oh, we have the vestibulocochlear nerve. What is the vestibular nerve involved with? Balance. The vestibulospinal tract has two components, and we'll look at those independently in a little while. A medial and a lateral tract. One is for position of the head and neck. The other is for balance. Frankly, the movement of your head and neck is also associated with balance. These two really work together nicely at determining where you are, where is your head, and how do you maintain balance. The reticulospinal tract, automatic posture and gait-related movements. Automatic posture. How many of you are putting any thought into how you're sitting in the chair and holding yourself in place? None. You're not. You're sitting there. That's automatic posture. You're putting no thought into that whatsoever. You're sitting there, you're upright. You learned how to do this when you were this big, and you're doing it yet today. Now, gait-related movements. I'm walking back and forth here. As I'm walking back and forth, am I thinking about moving my left leg, my right leg, my left leg, my right leg, my bend, flex, extend, No, I'm not doing any of that. But, with rare exception, I'm being moderately successful. I'm not bumping into things, I'm not tripping, I'm not falling, I'm not going right, left, right. I'm getting the order of movement down. Everything seems to be working. And that involves the reticulospinal tract. So the reticular formation, once again, we touched on that earlier. We're going to be revisiting that. And then the tectospinal tract, the tectum of the brain, the midbrain region. Coordination of head and eye movement. There's a lot involved with that. It's football season. Do anybody still watch football anymore? Even after this last weekend, you don't watch the Lions, you watch somebody else. Yeah. Watch a receiver going out to catch a pass. It's amazing, it's mind-boggling. When you start watching sports, thinking neuroanatomy, you have attained full-fledged geekdom, okay? You are now officially weird. Watch that runner. He's running, okay? As he's running, is he thinking about his legs? No, he's not. Gait-related movements. He's twisting his torso. Oh, torso. Those are those axial, biaxial, or bilateral axial and girdle muscles twisting. Extending his arms, looking up, watching the football move, tracking it with his eyes, moving his head, catching the ball, all the time, if he's good. Not tripping and falling over his own feet. That's mind-boggling. It's crazy. You shouldn't be able to do it. Years ago, a bunch of us from the neuroscience program at U of M, end of the long week, went out to the bar, have a few drinks. We're sitting there, watching a baseball game. Pitcher throws a pitch, batter hits the ball, 100 mile an hour, line drive right at the pitcher's head. Okay? Now, if you've ever played baseball, you know you don't have a lot of time to react. Pitcher throws the ball, does this. There was no time to think. We did the calculations. There was not a thought involved. Okay? But there was one important thing. If he didn't do that, he would have died. fraction of a second. Contralateral limbs worked wonderfully. Head and neck, eye muscle control, beautiful. Axial, girdle muscles, great. His balance, wonderful. He used every system in here to live to pitch another day. Amazing. When you watch sports knowing what goes on in the brain, all of a sudden it's totally different. The game takes on really weird dimensions. I expect you to know what each of these tracks is responsible for. Okay? Now, tracks, descending motor pathways. The approach that you should take. Number one, where does the pathway start? Number two, how many neurons are involved? Number three, where do synapses occur? And number four, where is a point of decussation? So,
can you repeat that one more time?
Okay. Where are the neurons where the signal starts? Where do synapses occur? Where's the point of decussation? There's another one, wasn't there? How many neurons are involved? So, we have the lateral cortical spinal tract. Most of you knew that's it right there. Okay? However, let's go to the origin of the tract. There it is. It's in the cortex. Oh, well, that's cool. This axon. Whenever you see this is a neuron. This is the cell body, the soma. This is the axon terminal. Wherever you have an axon terminal, what else are you going to have? You're going to have another soma and a synapse. All right? Cool? So, the minute you understand that, when you look at something like this, you will automatically know whether it's somatosensory or motor. I don't have to tell you anything else. I can just show you the picture. Now, how do you know this is a motor tract instead of a somatosensory tract? Yeah?
Because it's descending.
It's descending, and the reason you know that is the cell body's up here, and this comes down, and synapses. All right? So as you look at these, look at where the cell bodies are, look at where the synapses are. So here we are, cell body, comes on down, decussation. That's the point where the axon and the signal crosses from one side of the brain or one side of the body to the other. This is the pyramid of decussation. This is on the surface of the medulla. So the signal crosses over, continues down, lateral cortical spinal tract. The synapse here is going to take place in gray matter. Why? What?
Neuron body. I mean,
You have neuronal cell bodies. If you're going to have neuronal cell bodies, overwhelmingly it's going to be in gray matter versus white matter. The tracks are in the white matter because they're myelinated axons.